The subject of this video is finding the length of a curve. We call this arc length. And the way we do it is we divide the curve into tiny little segments. If the curve is differentiable, then the curve can be approximated by a tangent line near any point. So this makes sense to do for differentiable curves. We can divide the curve into tiny little segments, each of which looks like a line. If we then just compute the length of that line and then integrate, we get the full arc length. And we're going to develop formulas for this, which you can simply then use, and you won't have to go through this process each time. So let's take a curve and let's zoom in very close to a certain point, and we get what looks like a line. Well, then we can draw the horizontal and vertical lines shown here to form a right triangle. And by the way, S is the traditional letter used to describe arc length for some reason. I'm not sure why, but it is, so we'll use that convention. But now using the Pythagorean theorem, I can write down ds equal to square root of dx squared plus dy squared. Now, to get a more useful form, what I can do is factor out dx squared from this square root, and I get this expression. ds is equal to the square root of 1 plus dy dx squared dx. This dx is outside of the square root. Now, this is useful if the curve happens to be given as a function of x, because then this dy dx is just the derivative of that function, and then this is an easy formula to use. Otherwise, I could also have taken this first formula and factored out a dy from the square root, and I would get dx dy squared plus 1, and then the square root of that, with dy outside of the square root. And this is useful if we have a curve which is given as a function of y. And essentially it's the same formula. You see, it's still just the derivative of that function squared plus 1 under the square root. And so really there's only one formula here. It's just the derivative of the function squared plus 1 all under the square root. Let's use this to find the arc length of the curve y equals x to the 3/2 from x equals 1 to x equals 2. First we take the derivative of the function. Here it is. And then we plug it into the formula. 1 plus the derivative squared is under the square root, and x ranges from 0 to 1 as stated here. And now this is a relatively simple integral. We can do a substitution, then rewrite the integral. And notice that I've changed the limits of integration here, so I don't plan to back substitute. And now to finish the problem, we simply compute the rest of this integral. Use the power rule, and then you plug in the endpoints and subtract them, and then simplify. And that's really all there is to it. This is the arc length of that curve. You'll notice that it's a rather complicated expression. This is true. This is actually quite typical. The integrals that you get using this arc length formula are often kind of tricky, but at least it is a formula that we can use. So let's remind ourselves what this formula was. If the curve is given as a function of x, where x ranges from a to b, then the arc length, the total arc length, is from a to b, integrating from a to b, of this square root expression, the derivative squared plus 1 dx. Or if the curve was given in terms of y, where y ranges from a to b, then it's, well, the same formula, still just the square root of the derivative squared plus 1. And then the integral is over the range of y values. In the next video, we're going to talk about the average value of a function, but before we do that, I want you to verify that this arc length formula does give the correct arc length for a circle. Now, the good news here is that you can check your answer because you know how to compute the arc length of a circle without calculus, so you'll be able to check your answer. So give that a shot, and I will see you in the next video.